or transformed, but it must always be conserved. When black holes evaporate through Hawking radiation, what happens to the information they contain? Is it released in the radiation encoded in forms too complex for us to decode? Or is it truly destroyed, violating one of the fundamental principles of physics? Recent research suggests that the interior of black holes might not exist at all. That what we interpret as a three-dimensional region of curved space, might actually be information encoded on the two-dimensional surface of the event horizon. This holographic principle implies that all the information we think exists in three-dimensional space is actually stored on two-dimensional boundaries, like shadows cast by higher-dimensional realities we can't directly perceive. If the holographic principle is correct, then the entire universe might be a projection from information encoded on some cosmic boundary, possibly the edge of the observable universe itself. Everything you see, touch, and experience might be a holographic illusion, a three-dimensional shadow cast by two-dimensional information processing on the surface of space-time. Your thoughts, emotions, memories, and consciousness might all be holographic projections from data encoded at the edge of reality, making you not a three-dimensional being, but a two-dimensional information pattern experiencing the illusion of depth and solidity. The holographic principle suggests that the question of what happens when the universe ends might be fundamentally misguided. If reality is information encoded on boundaries rather than matter distributed through space, then cosmic endings might be transformations of encoding rather than destruction of substance. The universe might not die. It might simply change the way it stores and processes information, transitioning from one form of holographic projection to another, from one pattern of boundary encoding to a different pattern that creates different kinds of experience, different forms of reality, different ways of being conscious. The problem of quantum gravity reveals the deep incompatibility between our two most successful theories of physics. Quantum mechanics describes the behavior of matter and energy at the smallest scales with incredible precision, predicting the outcomes of experiments to more decimal places than any other scientific theory in history. General relativity describes the behavior of spacetime and gravity at the largest scales with equal precision, accurately predicting everything from the orbit of Mercury to the existence of black holes and gravitational waves. But these two theories are fundamentally incompatible. Quantum mechanics treats spacetime as a fixed background against which quantum events occur, while general relativity treats spacetime as a dynamic entity that curves and flexes in response to matter and energy. When physicists try to combine these theories to create a quantum theory of gravity, the mathematics breaks down into infinities and nonsensical results. Every attempt to merge quantum mechanics and general relativity reveals new paradoxes, new impossibilities, new ways that our understanding of reality contradicts itself. This incompatibility isn't just a technical problem. It's a sign that our entire conceptual framework for understanding reality might be fundamentally flawed. We might be like ancient astronomers trying to understand planetary motion using the assumption that Earth is the center of the universe. Not wrong about the details, but wrong about the basic structure of what we're trying to explain. The search for quantum gravity might require us to abandon some of our most basic assumptions about the nature of space, time, matter, energy, and causation itself. String theory and loop quantum gravity represent two different approaches to resolving these paradoxes, but both require us to accept ideas that seem to violate common sense. String theory suggests that particles are actually extended objects vibrating in 11 dimensions, most of which we,